Okay, so today we're going to be talking about z-test and t-test. Now, z-test and t-test are parametric tests of difference, which means they sort of require normal distribution. So in these two types of tests, what you could expect are hypotheses that include number one, is there a significant difference between, and number two, is A better than B if it's a directional test. So again, the first hypothesis would be very much applicable for non-directional hypotheses. And then you have your number two, which is applicable for directional testing. Now, as a parametric test, we have a strict set of assumptions. Number one is that the data should be measured in the interval or ratio scale. So as long as it is a continuous variable, then we are safe to use z-test and t-test. But again, ideally, we would like and prefer that it's in the ratio scale. Okay. Number two, there should be no significant outliers. So if the mean is, for example, 108, observations must be close to that value. So that means that at least in the normal distribution curve, there are no significant outliers or you have no data that are very far away from our mean. So that would be the meaning of number two. Number three, the data should be approximately normally distributed. Now we do have, excuse me, we do have statistical tests for normal distribution, but for this, I would just like to mention that to approximate the normal distribution of a certain data set, all you have to do is make sure that the mean, median, and mode is approximately equal to each other. So for example, our mean is 108, then our mode and our median should be at least close to 108, if not exactly equal. Okay, so that would be the meaning of approximately normally distributed. Okay, so in our test and in our testing, we're going to mention if we have to assume normal distribution or not. Okay, let's start with our z-test. So z-test is used when the population and sample size exceeds 30. So n should be greater than 30. And t-test is used when the sample size is lower than 30. So n is lower than 30. So this is for t-test. Okay, so there's not much more to say about these two different tests. Let's try and have an example. But first, let's show the formula for z-test or z-test. Now, the formula for z-test is relatively simple. You have your one sample, z-test, sorry, one sample, and your two sample, z-test. So again, let's just have a sort of a legend for our formula. You have your sample mean, then you have your population mean. For n, that would be your sample size. By the way, these are all written in the transcript that I sent you, so please do refer to that if you find this a bit confusing, so you have your own reference. And your omega is your standard deviation. Same goes for two sample t-tests. The only difference is that here we have the mean of group A and group B. Okay, and then here you have your hypothesized mean difference. Hypothesized mean difference. Okay, so the difference between the two is that for one sample t-test, you only have one set of samples. That means this could either be a pre-test, post-test situation. So, for example, you have group A with 5 samples. Then you would have group A for 5 samples for both pre and post testing. That's the population and the sample mean. So you only have really an n of 5. Unlike with your two sample tests, you have group A and group B, for instance, and each would have 5 samples each, then you have a total observation of 10. So the difference is for two sample t-tests, you have two different groups or two independent groups, whereas in one sample t or one sample z-test, you only have one specific group, which you test twice or you measure from twice. So again, this could be a pre-test and post-test situation depending on your data. Next, let's move on to the legend for our denominator. You have your omega here, which is again your standard deviation for both group 1 and standard deviation for group 2, depending on the subscript. Okay? And then we have to square that standard deviation and divide it by n1, which is the sample size of group 1. And so it follows that n2 is the sample size of group 2. Okay? So it's really no use to learn the formula if we don't have to try to have an example. So let's have this sample problem. Now, a manufacturer claims that the average tensile strength of a thread A exceeds the average tensile strength of thread B. Now, type A had an average tensile strength of 86.7 kilograms with a standard deviation of 6.28, while type B had an average tensile strength of 77.8 and a standard deviation of 5.61 kilograms. Now, the manufacturer provided 50 samples each, and the manufacturer claims these numbers at 5% significance. Now, the first thing that we have to do, again, in statistical hypothesis testing, is that we have to analyze the problem. Now, here, a manufacturer claims to be comparing two different types of thread. So you have thread A and thread B. So automatically, we know that we're going to be using two sample z-test. Okay. Now, type A had an average tensile strength of 86.7. That would be our population mean. And a standard deviation of 6.28. So this would be our standard deviation for group 1. So 6.28. And then you have your type B with a standard with an average tensile strength of 77.8 and a standard deviation of 5.61. Now, the manufacturer provides 50 sample each, so N1 is 50, so is N2. Okay, total of 100 samples. And also, of course, we cannot forget about our alpha, which is 5% or 0.05. Okay. So again, saan ko po kinuha yung mga values natin? Kinuha ko lang po siya sa ating problem. So you have 86.7, you have 6.28, 77.8, 5.61, you have 50 samples each, and an alpha or 5% significance. So that would be analyzing the problem. Next is that we have to formulate the hypothesis. So again, the manufacturer claims that thread A, notice the wording, exceeds the average tensile strength of thread B. So when we formulate the alternative hypothesis, we say thread A exceeds thread B. And to represent that mathematically, you have thread A is greater than thread B. Okay. Next, for your null hypothesis, thread A is not or does not exceed thread B. Again, we have to represent that mathematically. So that's A is less than or equal to thread B. Okay, so that is simply how we formulate our hypothesis. You look for the statement, you have thread A, we're comparing thread A and thread B. So what we now know is that we're looking for difference between the two. Now, next thing to do is to see if the test is directional. So exceeds is a very directional term, so which means that you are claiming that thread A is better than thread B. So therefore, thread A exceeds thread B. Mathematically, we represent it as such, and the null hypothesis as such. Okay, simple as that. Next, we have to determine the tails of the test. So a manufacturer claims that the average tensile strength of thread A exceeds the average tensile strength of thread B. Again, paulit-ulit na po tayo. We know that this is a one-tailed test. Okay? So how did we know that this is a one-tailed test? Because we have a directional term that says A is better than B. Okay? And this would also be a good time for us to determine the critical value of Z. Now, we can use a table for to look for the critical value of Z, because Z-test is based on the areas under the Gaussian curve, or the areas under the normal distribution curve, which for simplification, I've already summarized, or I've gotten a picture that summarizes the critical values of Z depending on your confidence interval. Now, these are the four confidence intervals that we're going to be most commonly encountering. So you have 90%, 95%, 99%, and 99.9%. Again, your z-test is one of the simplest statistical tests of difference, and so its critical value is based simply on the area under the Gaussian curve. So if you have 95%, which in our example is our confidence level, we're going to use a z-value, or a critical z, of 1.96. Now let's try to illustrate that using the Gaussian curve. Here is the Gaussian curve. So in this example, we know, or rather in our previous lecture of statistical hypothesis testing, we found out that each side is equal to an area of 0.5. Okay, and the whole curve has an area of 1.0. Now, since our z-test is based on, well, the areas under the normal curve, we have to find out where 1.96 is. By the way, again, 95% confidence interval would use a critical z-value of 1.96. Okay, so we have to find out first where or which tail we're going to use. Would it be the left or the right tail? In this case, all we have to do is pull out our alternative hypothesis, which is A is greater than B. And I've already taught you how to quickly determine which tail we're going to use. All you have to do is simply look at where this arrow is pointing. In this case, it looks like an arrow that's pointing right, and therefore we're going to use the right tail. Just imagine that our x-axis has 1, 2, and 3. You have -1, -2, and -3 on the left. Since we're going to use a positive tail, 1.96 remains to be positive. So all you have to do is look for where 1.96 would be. This is 1, 2, and 3. 1.96 would probably be around this area. There. So therefore, your area of rejection is over here. This is 1.96, which is also the critical value of Z. And this whole area over here to the left would be your area of acceptance. Okay, so for this hypothesis, to be true, for A to be exceedingly better than B, then our test statistic should fall within the area of rejection. Otherwise, we have to accept the null hypothesis, which again states that A is less than or equal to B. Okay, so this is what we're going to use to be able to decide on a conclusion regarding our null hypothesis. So remember, even though we formulate our alternative hypothesis first, we still act on our null hypothesis. So si null hypothesis, either accept or reject, depending on where our computation falls within the Gaussian curve. May it be in the area of rejection or the area of acceptance. Okay, so let's try on our test. Okay, so now we have to select the test and compute. Again, we have two options. Since we're looking for difference, we could use z-test and t-test. But as our analysis of the problem showed us, we have a sample size of 50, which means that our n is greater than 30, and therefore the favorable test for us to use is the z-test. Now, there is the issue of choosing whether we're going to use one sample or two sample. And since we've already established that one sample t-test or one sample z-test is just one group of samples, and two sample z-test uses two groups of samples. In this case, we have thread A and thread B, so we have two different samples, so we have to go with two sample z-test. And the formula is as follows. You have the difference of means. You have your hypothesized mean difference. You have your standard deviation of group A, of thread A, standard deviation of thread B, and you have your sample size of A, you have your sample size of B. Okay, so now that we've established what test we're going to use, we can then perform the test. Now, in this example, it's very well noted that all of the variables are already given, so you don't have to do any additional computation. You have the mean of group A, you have the mean of group B, standard deviation of group A, standard deviation of group B, you have n, and you have your alpha. So all you have to do really is substitute. So again, all we have to do is substitute. So we have to substitute 86.7 minus F77.8 minus our hypothesized mean difference, since our null hypothesis is A is less than or equal to B, then U1 or mean 1 and mean B would be the same or equal. So therefore, this is 0. So next, you have your standard deviation of group A, which is 6.28. Standard deviation of group B, which is 5.61. And both sample sizes are 50. And all you really have to do after that is take the computation. So let's try. Okay, so we've done this from the previous part, so I'm just going to skip this slide. Next is we have to perform the test. Okay, so performing the test is relatively simple since we've already substituted our variables. So you have 86.7 minus 77.8, close that in a parenthesis, minus 0, which is our hypothesized mean difference, divided by the standard deviation of A, which is 6.28. Don't forget the squared, divided by 50 plus the standard deviation of b, which is 5.61. Don't forget the squared divided by 50. And all we have to do is compute. So 86, let's try a different color. 86 minus 77.8 minus 0 is simply 8.9. Divided by, let's try them one by one first, the square root of the 2. So you have 0.79 plus 0.63. Now I'm rounding off to two decimal places here. So this actually has more numbers or more decimal places. This is 788,768, and this one is 0.629442. Okay, but for the purpose of simplicity, I'm rounding off to do two decimal places. But when you're using your calculators, I would advise you to, of course, take the whole value until the computation is finished. Okay, so now that we have this, all we have to do is add. By the way, this is these terms already. All we have to do is add. That's 1.41. Move it here. So 8.9 divided by 1.41, but we still have to deal with the square root. So that's 8.9 divided by 1.19. And our final answer would be 7.47. So this is our z value or z stat. Okay, so it's as simple as that, especially for z-test. When you're already given all the different variables, all you have to do is substitute the different variables and use your computation. Okay, so next, after performing the test, we already have our z value of 7.47. All we have to do now is conclude. Now again, our confidence level is 95% owing to the fact that our alpha is 5%, which is 0.5. So our confidence level is just the inverse of your alpha, that is 95%. So we're going to be using 1.96 as our critical z value. And remember, since we're doing a one-tailed test, from our alternative hypothesis of A is better than B, arrow is pointing to the right, so our critical value is over here. And the threshold is 1.96. Okay, our computed stat or z-stat is 7.47. Okay, so 7.47 is way up in the right tail, and therefore we fall within the area of rejection. Remember that when you're doing conclusions, if your computed z-stat is greater than your critical z, then reject. If your z-stat is less than your critical z, and then accept. Okay, because for instance, let's say that our z-stat, example lang, our z-stat is negative 1.8. So our negative 1.8 example z-stat is going to fall over here, which is well within the area of rejection, especially since we're doing a one-tailed test if A is better than B. So if that's the case, then we fall within the area of acceptance. But since we're doing a one-tailed test, we can simply do, or rather, since our computed z-stat is 7.47, which is significantly greater than our critical z of 1.96, then what we can do or what we should do is reject the null hypothesis. Okay? And remember, our null hypothesis is A is less than or equal to B. So this is rejected, therefore A is better than B. Okay? So A is better than B. And this, ladies and gents, is our conclusion based on our statistical test. Now that illustrates a lot about how difference and significant difference differs when it comes to conclusions. So there is a difference, yes, of course, but if it's not statistically significant, then it could not be presumed to be consistent within the certain set of parameters. That means that, for instance, you see a difference in one tire or one thread, thread A, you cannot simply say that thread A is better than thread B. You have to have a larger sample size, and you have to have a statistical analysis. That way, you have mathematical and statistical proof that your thread A is indeed better than thread B. Okay, so that would be our conclusion. Next is our one sample Z test. Now, this is quite a lot simpler when it comes to computations because it has. Next is an example for one sample Z test. Now, one sample Z test, contrary to what was mentioned earlier, is a test we use when we want to see if a certain value or a certain average, in this case 6.7, is greater than or equal to a hypothesized value, in this case 5. So let's have the example. 1,500 women follow the Atkins diet for a month. A random sample of 29 women, this is already your N or your sample size, gained an average of 6.7 pounds. So this is your X bar, or this is your actual value. Test the hypothesis that the average weight gain per woman for the month was over 5 pounds. So this would be your mu, or your hypothesized value or hypothesized mean, and the standard deviation for all women in the group is 7.1, which is your omega or your standard deviation. So now that we have all the values, by the way, I'm still following the steps of statistical hypothesis testing. In this case, I'm just being fast with it. But for your case, if you're not yet used to doing it this way, I would advise you to follow the step-by-step procedure. So after we've already identified and analyzed the problem, all we have to do now is formulate our hypothesis, starting with our alternative, which is the hypothesis that the average weight gain per woman for the month was over 5 pounds. So our hypothesized mean is greater than 5. Okay, and our null hypothesis is less than or equal to 5. So I'm not writing it anymore. I'm just using the mathematical representations. And then we have to decide the tails of the test. In this case, as I mentioned, since we're using a directional hypothesis, then we're going to use a one-tailed test. And to illustrate that, let's have our Gaussian curve. So imagine nyo na lang po na this is a perfect normal distribution curve. Okay, sorry about that. And since we're using 95% confidence level, that corresponds to an area of 1.96, again, from the table before, and our alpha would be 5%, or 0.5, or 0.05, sorry. And our 95% translates to a decimal value of 0.95. Now, bisect it in half again. Mark your area of rejection, which is around here. So that's 1.96. This is your area of rejection. And the rest, of course, is your area of acceptance. Okay. So that we have all the formalities out of the way, all we have to do is identify the test that we're going to use. In this case, we only have one group of samples. So one sample, Z test. And the formula is as follows. So Z, or your Z score, is equal to the quantity of your mean minus your hypothesized mean times the square root of our sample size divided by our standard deviation. So since all of those are already given, we don't have to do any additional computations. All we have to do is substitute the variables. In this case, our mean is 6.7. That's minus 5 for our hypothesized mean times the square root of 29, which is our sample size. So all divided by the standard deviation, which is 7.1. So all we have to do is compute for the values. So you have 1.7 times the square root of 29, which I believe is 5.39. And all divided by 7.1. Now, further performing the operations, you get 9.15 divided by 7.1. Again, just a disclaimer, I'm rounding up to those two decimal places just for the convenience of writing it on the PowerPoint presentation. It might take too long if I write all the digits, but for your purposes, if you're computing manually for a z-score or a t-score, all you have to do is input the formula in your calculator or input the values into your calculator, and it's going to compute it with all the decimal places that are in that computation. Okay, so when you're computing, do not round off. Please do round off in your final answer at two decimal places. So what we get here is 1.29 or 289. Okay, so this is our z-score. And as you can see, our z-score is less than 1.289 is less than our critical value of 1.96. So therefore, our z-score falls within the area of acceptance. So therefore, our decision is to accept the null hypothesis. Okay? Now that would be our one sample Z test. Now, there are other things that you have to consider. Like for example, you could search up 1.289 in our Z table, and you're going to find out that the area it occupies is around 8997, if I'm not mistaken. And if you compute for the p-value, simply subtract that from 1, then the area that it occupies is 1.0 or 1003, 0.1003. And this would be, again, in our p-value comparison, 0.1003 is greater than 0.5, which is our alpha. So therefore, it's just right that we reject the null hypothesis. By the way, this is the probability that your data falls within the parameters that the problem has set. So in both cases, 1.289 using the z-score and the p-value, we have to accept, or rather we have to conclude and accept our null hypothesis. Okay, so that is your one sample Z test. Okay, next we're going to talk about t-test. Now, t-test is another test of difference, but this time it's used for situations where our n, or our sample size, is lower than 30. Now, we have two formulas that we can use for t-test. The left one is used for our, two sample t-test, or also referred to as your independent t-test. And then the right one is used for your one sample t-test, or sometimes referred to as our paired t-test. Okay, so let's try to discuss the formula a bit. You have your mean of A. This is the average of your A or set A. It's average of your set B. This is the sum of squares, which means that you have to square each observation and add them. Okay. Next, this is minus EA, or the summation of A, or all the observations in group A, and then squared divided by the sample size. Plus, same thing, the sum of squares of set B minus the sum of all observations of set B squared divided by the number of observations. Now this will all be divided by n, or the number of samples in group A and the number of samples in group B. So, sorry, I must have written a letter number 8 minus 2. So that would all be multiplied by the fraction 1 divided by n, or the sample size of A, plus 1 divided by the sample size of B. And all you have to do is take the square root of that value. Okay? So a bit complicated well, when you're looking at it, but when you're actually performing the test, it's quite simple. For paired t-test, all you have to do is get the sum of differences. So this would be the sum of differences divided by n, which is our sample size, over the square root of the summation of differences squared. So again, the sum of squares of the differences minus the sum of the squared. So you're going to notice that this is awfully similar to the two terms we have in our independent samples t-test, over this, by the way, is referred to as our degrees of freedom. N minus 1 times n. This would also be our degrees of freedom. So NA plus NB minus 2. And this degrees of freedom is going to be useful when we are trying to determine the critical value of T. So that would be the formula for the t-test that we're going to be performing in our midterms. Next, let's have an example. So, example, the test scores of two groups of students are posted on the table. Test the hypothesis that there is no significant difference between the set of scores of both students group at 5% alpha. So first, let's analyze the problem. So the test scores of two groups, we're comparing test scores. We know that there are two groups of students, and the data is posted over here. So you have your group A and group B. Test the hypothesis that there is no significant difference between the set of scores of both student groups at 5% alpha. Now, in this case, the null hypothesis has already been given. So when you formulate your null hypothesis, it's simple as U of A, or the mean of A, is equal to the mean of B. So that means that there is no significant difference. Next, we have to formulate our alternative hypothesis, which is simply the same, U of A, but this time not equal to the mu of B. Okay, so that would be our null and alternative hypothesis. Now, it's mentioned that we have 5% alpha, so our significance or level of confidence is 95%, and our alpha is 5%, or 0.05. Next, we have to determine the tails of the test. We know that we are only looking for significant difference. There is no direction. We're not assuming that A is better than B or B is better than A. So therefore, this would be a two-tailed test. Okay? Again, this would be very significant and important when we are trying to determine the critical value of t. Okay. Now, another thing that you have to mention, or another thing that you have to learn, is when we're testing for difference, sometimes we have to compute for degrees of freedom. Now, this would be important in determining the critical value, but for now, let's try to compute. So for degrees of freedom for t-test, all you have to do is get the number of samples and subtract by 1. But since we have two groups, we also have to add the groups first. So that would be NA plus NB minus, since again, there are two groups, minus 2. So that would come out to, we have 10 observations per group. So N of A, or our sample size for A, is 10, plus the sample size for B, which is also 10, and subtract it by 2. That would give us 18. So our DF, or degrees of freedom, is 18. Okay? So then, now that we have all the different information we need to compute, let's try and proceed with the computation. Okay, so again, this is your data set. And what I like to do is first compute for the total and the mean, or the average per group. And if you would like to emulate my manual computation for t-test, what I really endorse doing is to create a table that has all the information you need. In this case, all you have to do is make the computations or perform the operations. Okay, so you have your group A. I have the total. This is our summation of A. This is our mean. You have your 65048. That would be your sum of squares. This would also be your sum of squares. And you have the summation of all the observations of B. This table would make it a lot easier for us to be able to compute our very complicated, not very complicated, our slightly complicated formula. Okay, so now that we have all the information we need, we can apply the formula. Okay, first, let's try and see if we're still lacking lacking values for our formula. So first you have the mu of A, or the mean of A, that's just 80. And then you have the mean of B, which is 79.4. You have the sum of squares, which is over here. So that's 65,048. You have the total squared, which is 640,000. You have number of observations for set A, that's 10. You have the sum of squares of B, which is 63,646. You also have the total of B squared, which is simply 630,436. Again, you have 10 for each of the n's. This n is simply referring to the sample size of set A and set B, depending on the subscript. Okay, so now that we have all the information and all the values we need, all we have to do is substitute our variables with our values. Okay, so our numerator would come out to 80 minus 79.4. That would be divided by the square root of a quantity of the sum of squares, which is 65,048, minus our total squared, which is 640,000 divided by 10, plus the quantity of our sum of squares for b, that's 63,646 minus 630,436 divided by 10, and that whole quantity is going to be divided by n plus n minus 2. So that's 10 plus 10 minus 2. Also again referred to as your degrees of freedom. Now this whole quantity is going to be multiplied to fraction of 1 over 10 plus 1 over 10. Okay, thankfully kumasya, but let's try to move on to our operations. So t is equal to 80 minus 79.4, that is 0.6, divided by 65,048 minus 640,000 divided by 10. So essentially that's 65,000 minus 64,000. That comes out to 1,048 plus 63,646 minus 630,436. That would amount to 602.4. Okay, so this would be added, but after adding them, we divide them by 18, and we multiply the whole quantity to 2 over 10. Okay, so if you can recall and remember the addition of fractions, all you really have to do is if they have the same denominator, you simply add the numerator. So this is 2 over 10. Okay. Further performing the operations, 0.6 divided by 104 plus 602.4. I'm not going to write it down, but that comes down to 1650.4. 1650.4 divided by 18 would come out to 91.69. Okay, so again, this is quite a shorthand version of the answer. So please do make sure that when you are computing, you include all the decimal places, since you'll be using a calculator. And a lot of you are probably going to input this formula directly into your calculator, and so that would be considered in the answer. Multiplied by or times 2 over 10, that's simply 0.2. Further performing the operation, you have 0.6 divided by 91.69 times 0.2. I think that comes down to 18.34. Okay. That would be equal to then oh yeah, I forgot the square root, so apologies for that. Make sure that you remember the square root. That would then equal to 0.14. Yeah. That would be the complete notation. So this then is your t-score. Okay, so quite a bit confusing when you're performing the operations one by one, but if you get to master inputting data in your calculator, then you're going to have an easier time. So I do advise you to take mastery of your calculator usage. Okay. So we already have our t-score. The next thing that we have to do is conclude. But first, we have to look for the critical values for t. So our critical value is supposed to be, for two-tailed, that is 2.101. Okay, this would be our critical t. Now, for our t-table, all you have to do is check if you're using a one-tailed or two-tailed test. Since we're using a two-tailed test, we're going to be using two-tailed degrees of freedom. So in this case, our alpha is 0.05, so we're going to be using this column. Okay. Next, our degrees of freedom is 18. Again, that would be n plus n minus 2. So n of A plus n of B minus 2. That's 10 plus 10 minus 2. That would come down to 18. So our degrees of freedom is 18. All you have to do is look at the intersection of the two, and you have your critical value, which is 2.101. Now, going back to our t-stat, which is 0.14013, I bet it's obvious that there is no significant difference between the two. Okay, but for now, let's try to illustrate that. So here is our normal distribution curve. We have a two-tailed test. So our critical value is going to be over here. This is our area of rejection, which is demarcated by 2.101, negative on the left side, and positive on the right side. And our computed t-stat is about 0.14, which is way in the middle. Okay, so therefore, our critical value or our t-stat falls within the area of acceptance, and therefore we have to accept the null and reject the alternative. Okay, so our conclusion, to make it a lot simpler, is there is no significant difference between the test scores of student group A and group B. Okay, so that would be our conclusion. Okay, so that about ends our lecture on our first two tests. You have your z-test, one sample and two sample, and you have your t-test, two samples. So the reason why was not able, or I'm not able to discuss or I did not discuss the one sample t-test or the paired t-test is because it's quite an easy formula for you to follow. So I hope you could use that as a training or a tool for you to improve your understanding of the different formulae we're going to use, because honestly, it's going to get a lot more complicated when we get to analysis of variance. So please do try and understand the formula for paired t-test, and we'll have an activity for that after. Okay, so that's it for today. Thank you so much for attending or for listening. I hope you learned something new, and I hope you've grasped the concept of our test of difference. Okay, so again, goodbye and thank you.